because it would come there with a vector x maybe 10 by 1, and you would try to multiply 10 by 1 by 10 by 1. You can't do that, and you get an error message. So what's very important over here is to, again, tell MATLAB that for each element of x, I want to square it, and that's what the document did, okay? And clearly, it's element by element. So what's the first element of f? E to the x1 minus x1 squared. Next element of f? E to the x2 minus x2 squared, etc. Okay? So you have to be careful when you code this up, okay? You have to do it in a way that the input x is a vector of x values rather than just a scalar. Okay. So let's go and see how well this thing does. Do I still have the graph there? Yeah. Okay. And just to show you how robust it is, I'm going to be sloppy. Okay. You can see where the root is, right? It's kind of minus 0.7 something. Let's give it minus 0.6. Okay, which is way off, but it's good enough that MATLAB will able to drive it to the right root. So let's take our starting value is minus 0.6. Okay. I mean, you can play it. I wonder if you gave it like 0 if it would even work. But you know, let's at least use. Okay. As a rule of thumb, take your initial value as close as possible to the root. Okay, but let's be lazy and do minus 0.6. Okay? Okay? So, I got my function over there, okay? And the way I do it, if you look at the documentation, the output is going to be the root estimate. So let's call that root equals, okay? Remember the function built into MATLAB is f0, okay? Now, what was the first argument to f0? That was this function, TREQ, that I coded up to compute this for vector x. And for some reason, MATLAB uses this thing called handles. You put an @ sign on there. I guess that distinguishes between just a symbol and a function, okay? So you put f0, okay? Not f0. What am I talking about? TREQ, right? That was the one that I computed, right? So now it knows basically, okay, what function f do you want to drive to 0? It's the one that's in the file, you know, TREQ.m, which is precisely e to the x minus x squared. Let's give it starting values at minus 0.6, I said. Okay? And see what it comes out for the root. Minus decimal 703, blah, 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 blah. Remember, we saw it was kind of close to minus 0.7. Okay? How well did this do? Well, let's compute f of x at that root that it just calculated. And again, you don't want to punch this in by hand. That's why I put root. Okay? Who will do that? Okay? TREQ. That's exactly what TREQ will do. TREQ will calculate f of x either for a single x or for a vector. In this case, TREQ of root hopefully should be very, very small. Right? And what do I get? I get machine 0. Okay? It's not, remember, it's not exact. It's this number, even though I've displayed a lot of digits, has more and more digits. It's, you know, the root is a transcendental number. Okay? You can't write it down as a finite or repeating decimal. Okay? And obviously, this can be used for functions that are much, much more complicated than that. Okay? So long as you can calculate your f of x, I don't care how complicated it is, at a given value of x, MATLAB will be able to find the root, provided you give it some estimate of the starting root. Okay? And just for the fun of it, let's try a really bad estimate of 0 and if that's going to work. So what did I get? The root equals. Okay, and let me give it 0. I'm not sure if this is even going to work because it's really off, but who knows? Let's see what it does. Yeah, even that was good, okay? Depends upon how oscillatory the function is and if there's going to be another root next to it, right? Okay. Well, if you have two roots that are, you know, kind of distance apart, you want a certain root, you want to be close to the root that you want, otherwise it's going to march to the other root. Okay. Okay, any questions on that? Again, always look at the documentation. There's plenty of examples. That's the great thing about MATLAB is they give examples of everything. And what's nice about it also, unlike many other languages, they don't give you the most complicated thing on earth. Okay, they give you very simple ones and gradually you know, get more sophisticated ones. Okay, so that's it for root finding. Let's do numerical integration. Okay, and again, I'm going to do one that you can do by hand so that we can check it. Okay, but obviously you would use this when you can't integrate it. Many times you've come across in practice integrals that you can't do analytically, definite integrals. Let's consider the integral from 0 to pi. What do I have here? X squared sine x. You can do that by integration by parts, and you can show that the exact value is pi squared minus 4, and that's approximately equal to 5.8696. The exact value is pi squared minus 4, and you're going to get a numerical value about 5.8696. Okay, so again, let's make believe I'm not here. You want to do an integral like that. Okay, you don't know where to start even. You go back over here to your little help, and you say, what most people call it integral, definite integral. Let's do integral. Oh, there it is, look. I even got a double integral it can do, okay? But what I want is numerical integration. Let me just do integral over there, okay? And you can see, let me blow this up a little. Control plus, will that do it? Push the option plus. Control plus. Yeah. Okay. Now that was no good. So I have to go down, so control minus. Okay? Hopefully you can read it, okay? So again, where it is, I'll read it to you. Okay, here's the syntax, okay? You want to integrate some function. It's no surprise that the first argument is the function or the integrand. So we're going to have to code up, just like we did for the transcendental equation, we're going to have to code up a function that, given a vector x of values, calculates x squared sine x. Okay, that's easy enough to do. Okay, and then you'll basically give it the function over there. And then, let's use the simplest form, the minimum value and the maximum value. In our case, that will be 0 and pi, right? So all we have to do is code up a one-liner that computes x squared sine x. And again, MATLAB assumes this can be a function. If you click over here, let me give you an example, okay? So, but I wanted to do one where you knew the answer, okay, so you can get faith in this. Again, this is the thing which I said, very early on in the course, that when you use mathematical software, and you're trying it for the first time, or you're trying a new routine that you never used before, do it on a problem that you know the answer for, okay? Not that the software is not reliable, but make sure you understand the right syntax, etc., for the input and the output. Okay, so let's just do that. Okay, and where did I do quad test? That's what I called it, quad test.m. These names are just suggested to me, that's all. Where did it go? Here it is, quad test, okay? Again, it's the same syntax, right? It's a function subprogram, so therefore the first word is function, okay? On the left you have your output, on the right you have the name. It could be anything that you want. I called it quad test, and the argument in this case has to be x. That's the variable appears in the integrand, okay? Obviously you could have called it t also, right? Doesn't make a difference, as long as y is computed correctly. Okay, so I want to compute, given x, the integrated, which is x squared times the sine of x. Same thing again. When you read the documentation for integral, that's the function that we're using, it requires you to write a function like this, and the x coming in will be a vector of values. Again, because it wants to do it very efficiently, right? You know when you do numerical quadrature, you find the area under the curve, okay? So what you do is you want to sample on the interval, okay, 0 pi, what this integrand looks like. So you want to give it a whole bunch of x's to see what goes on. And, we can get to numerical analysis, but most of these things use what's called interpolation type things. Like Simpson's rule, you probably learned in calculus, it will take this integrand over here and fit a parabola to it, okay, things like that. Okay, so obviously the function, and this is much more sophisticated than Simpson's rule, it's going to sample the function over various points of the interval, and to do it efficiently, it's not going to keep calling it with a different x all the time. It comes in there with one huge x vector and say, okay, for each element of that x vector I'm coming in with, compute x squared sine x. Okay, so I have y equals, okay, now notice I did x dot squared again, right? Because I don't want to take the vector x and multiply by itself, I want to do an element by element multiply. So what x squared is actually, it's a vector. It will be x1 squared, x2 squared, x3 squared, depending upon how many. And I want to do a multiplication of that by the sine of x, okay? And notice there's a dot again, okay? Everyone understands the dot before there because I want to get the square of the elements of x. But just think about it. What is x dot squared? It would be a vector. It would look like this. Let's say it's a column vector, and it has 3 elements. It would look like x1 squared, x2 squared, and x3 squared, okay? So it's going to be a 3 by 1. Now, Sine of x, again, just like the exponential, is vectorized in MATLAB. So MATLAB understands that if you come in with a vector x, okay, and you want to take the sine of that, it's going to take the sine of every element of x. So the sine of x, what's that going to be over there, what's connected to be, is going to be basically a vector. It's going to be the sine of x1, the sine of x2, the sine of x3, right? And what do we want to do over here? We want to do x1 squared sine x1, x2 squared sine x2, x3 squared sine x3, and put that into y, which in this case would be a 3 by 1, okay? And there you can see, therefore, that before the star sine x, you see right there before that multiply, there's a dot, okay? Because I don't want to multiply this vector by this vector. I want to take that array, x1 squared, x2 squared, x3 squared, and multiply term by term, right? And that's what the dot is on the multiplication, okay? So it's the same thing again. Like I said, most people, when they use these things and, you know, it's a problem with work, it's usually something like that, okay? So and that's kind of the first thing to look out for. Maybe you did something wrong. And you're fortunate if the program blows up and it does, you know, it gives you an error message. Sometimes, you know, it won't, and then you'll get a result that's completely erroneous because it's not doing what you want it to, okay? But most of the time we do things like this. If you did, for example, x squared sine x, and you left off the dot, either on the first x or before the multiplication, you get an error message, because it can't multiply two vectors. It can't multiply a 3 by 1 into a 3 by 1. Okay, linear algebra doesn't do that. Okay. So we're finished now. Okay, we got our integrand. Okay, let's see how close we come to 5.8696. Okay. Matter of fact, let's do this even, you know, a little more fun with this. So I got that integral right, and do I still have format long on? Hopefully I do. Let me say exact is pi squared minus 4, right? So I just did on the board to limit. I want to get this to full precision over here. See how good the integrator works. Pi squared minus 4 is exact. Okay? So 5.8696 and a whole bunch of digits after that. Okay? And let's call the one that MATLAB will compute numerically the approximate one. So we'll call it APP for approx. Okay? Okay? Well, remember the function is called integral, right? We just found that out. Okay? And the first argument is what's called a function handle. And who did that? It was called quad test, right? So I do at quad test. Okay? That's what computed this x squared sine x, the integrand. Okay? And then I think the next things are the limits of integration, which in our case is 0 to pi. Okay, 0 to pi. Okay, let's see how good that does. Okay, you can see C exact and C approximate. Pretty good, right? Matter of fact, let's see what the error is. Take exact minus approximate. Oh, I didn't spell it right, sorry. Exact minus approximate, I call it APP, right? 10 to the minus 16. Okay? So it's basically, you know, right on, right? Okay. Now, I should warn you though that, you know, this x squared sine x, if you graphed it, because 0 and pi is nice and smooth and stuff like that, many times you get things that you have to integrate where it's kind of oscillatory and stuff like that. Okay, it's not so simple. You have to put in these little options and stuff, or maybe break up the interval. Use, you know, like I said, always a good numerical analyst is a synergy between using a good code and also the way you present it, the analytics of the thing. Okay, this thing was simple enough that you have to do anything. You use the simplest default, and you got it to, you know, basically right on. Okay, so. And again, I wanted to do a problem where you knew what the exact answer was, so you can get some faith in this. Okay. The last thing I'm going to do today is solving differential equations. Okay, because that's what our course is about, right? And let me start with a simple differential equation. Not simple, a nonlinear one, which I don't even know what the analytical solution is. Okay, because it's too complicated. Okay. And this is probably one of the most sophisticated of all math. I should say sophisticated in the sense that, you know, the most documentation you'll find probably is on numerical solving of differential equations, because it's such a common thing, and also it can be very challenging at certain times. Okay, and you'll see there's a whole bunch of these called solvers that MATLAB has. Okay, We're going to use one called OTE 45, okay? The 45 does signify something about the order, but we won't get into that. There's also things that you may find when we go to the documentation. You'll see things called stiff solvers. What's stiff solver? There are certain applications, for example, in atmospheric physics or in chemical kinetics, where you have different reaction rates, and they have a very large range. Some certain types of reactions occur at a relatively slow rate, others at a very large rate. Now, normally what would happen is that when you do an integration, classically, you're always limited your time step by the highest reaction rate, right? One thing goes very slow, you can take a big delta T. Something goes really crazy and oscillatory, you have to take a small delta T. So what happens is that when we have these type of problems, they occur a lot in what's called mixed type flow problems, okay? It's very annoying because you have certain parts of the solution that don't change very rapidly and others that do, okay? And if you use the classical numerical solvers, you'd be limited by taking the smallest time step because of that rapid changing variable. Stiff solvers are designed to get around that, where it allows you to take large time steps for the variables that kind of evolve slowly and small time steps for the others. So I'm just telling you what stiff solver is so that if you see it, you say, what's that stiff mean even, okay? But we're not going to get into that. We're going to use the simplest solver that we have. But let me write down the differential equation I'm going to try to solve over here for you, okay? It's a first order differential equation. It will be dx dt. Again, it's not always going to be dy dx, okay? Is equal to, make it nonlinear, x squared minus t squared over t to the fourth plus 1. I just made this thing up, okay? There's no way you can solve that analytically. It's nonlinear. It's got that x squared in there, okay? And I need an initial condition. Again, initial conditions don't have to be 0. I'm going to say x evaluated at t equals -2 is 0.55. Okay? Let's try to solve that, okay? And I think you'll admit that that's all we need. If we have a first order differential equation, we only need one initial condition, okay? So basically I want a solution, somehow the curve should go through the point t equals -2, x is equal to 0.55. Okay. Well, again, I know nothing about how to solve differential equations, so I go back over here to the top, okay? And I'll put in differential equation.